let's spend a little bit talking about synthesis of alcohols. We'll go through this pretty quickly because a lot of this is review from last semester, but it's important that we have this down. These are going to be reactions that'll be important for us in doing multi-step synthesis in this unit. So let's review up on these, and this chapter just conveniently puts them all in one place for us. So look at everything we can do with alcohols. And we can go back and forth into most of the functional groups that we know of. Okay, we haven't gotten into any of the nitrogen-containing groups yet, but pretty much all of these oxygen-containing or non-oxygenated, like alkene. There are reactions to go in the forward and reverse directions from alcohols. So let's just start with synthesis of alcohols based on the things that we already know. If we have an alkene, here's 1-methylcyclohexene, we can make an alcohol out of that by hydration, right, which is just the addition of water across a double bond, right? Here's H on one, here's OH on the other. Here's OH on one, here's the H on the other that was added. So hydration is the addition of water across the double bond, right? So even though H2O isn't necessarily a reactant in this, the net effect is H on one, OH on the other, and double bond becoming single bond. So we can do it two ways. We can do it Markovnikov or non-Markovnikov. The Markovnikov way is where the OH is added to the more substituted carbon. So we do Markovnikov by the oxymercuration, demercuration sequence. So step one is mercury acetate, HgOAC2. Okay? That adds the OH on one carbon, the mercury acetate group on the other carbon. The OH is in the Markovnikov position. And then demercuration is a hydride, okay, where this H- displaces the mercury. So if you remember the name, oxymercuration, demercuration, you've essentially got the mechanism. You don't need a mechanism for this, but this intermediate here is important with the OH on one carbon, the mercury on the other. The non-Markovnikov addition starts with hydroboration, just like it sounds, H on one carbon, BH2 on the other carbon. In this case, the H is in the Markovnikov position, the BH2 is in the non-Markovnikov position. So hydroboration and then oxidation, where the BH2 gets replaced with the OH, but now in the non-Markovnikov position. Regiochemistry is Markovnikov or non-Markovnikov. That's where something gets added. Stereochemistry is important because in the hydroboration, the H and the OH are added on the same face. So that's a syn addition. There's a transition state where as we're adding the H and the BH2, they come from the same transition states. They're added at the same time as each other. Whereas in oxymercuration, we start with a mercury ion, a three-membered ring that's opened by hydroxide, essentially, by water, I guess. But stereochemistry is not important in oxymercuration, demercuration, because the H is added to the carbon that already had an H, so that's not a stereocenter. The stereochemistry is important in hydroboration because the H and the OH that we add end up on the same face. So that in turn determines what the relationship of the OH you added with the R group that was already on that other carbon. So make sure you're able to understand that. We can make 1,2 diols, either cis or trans. The cis diol comes from osmium tetroxide. It forms this osmate intermediate with two O's going the same direction, which is broken up. It's reduced by bisulfite. NaHSO3. So it's a reducing agent. It adds the H's to those. It breaks up that cyclic osmate and puts two OHs on one side. To get a trans diol, we use peroxy acid. right? They just say in general RCO3H. C double bond OH is a peroxy acid. MCPBA is the most common. And thanks to our aromatic chapter, that name makes sense to us now. Okay? Metachloro, so, right? Peroxybenzoic acid. So regular benzoic acid would be COOH. Peroxybenzoic acid is C double bond OOH. Metachloro peroxybenzoic acid. So MCPBA is the most commonly used reagent. That makes an epoxide, a three-membered ring where that double bond used to be. H3O plus adds to it, opens the epoxide, so it comes from, so the OH that we've added comes from behind, okay, giving us a trans 1,2-diol. Okay? So cis-diol with osmium with OSO4 and bisulfite. Trans diols come from epoxidation and then acidic hydrolysis to open it up.